Alright guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we talked about the differentiation technique known as implicit differentiation. We talked about when we would use that technique, and we saw some sample problems with how do we use that technique of implicit differentiation. In this video, we are going to touch on the derivatives of the inverses of functions, and we're going to use a theorem in here as well as implicit differentiation to learn what are the derivatives of some of our inverse trig functions. So we're going to work with a function f of x, and suppose that f of x is invertible. That is, the inverse function does indeed exist. Just a quick little recap on what the inverse function is and how it works. If f of a is equal to b, and we know that the inverse function exists, then by definition, f inverse of b is equal to a. So it's just a quick little recap on what it means. What is the definition of the inverse function? It says that if f of x is equal to y, then f inverse of y is equal to x. And we want to know, how can we come up with the derivative of this inverse function? Well, there's a special theorem out there. It's called the Inverse Function Theorem. And the Inverse Function Theorem tells us that under certain conditions, we can figure out what the derivative of the inverse function is, either at some particular input or just the general function overall. We don't typically concern ourselves in cases where the conditions aren't met, so we only work with those nice cases where we can use this. And what the theorem tells us as far as our formula is for the derivative of the inverse, it says that d dx of f inverse of x is equal to 1 over f prime of f inverse of x. So you have your function f, you have your inverse function f inverse. You're going to differentiate f, you're going to find f prime of x, and then you're going to take the composition f prime, circle f inverse. That's going to be the denominator of your fraction. In the numerator, you're just going to have a 1. Now, this formula, not typically something that we see very often, not something that we typically use that often, but this theorem is worth saying and mentioning here and noting because this is the special case of a more general inverse function theorem that scales up to functions of multiple variables and vector functions. That's something that if you go on to take more advanced math courses, you will learn about that later on. Now, this particular version of the inverse function theorem here, for certain kinds of functions, it's easy to check and see that you do indeed get the left and right hand sides to match. It's not so easy in some other cases. A couple examples where it is fairly straightforward to check. If you have x raised to the nth power, its inverse is x raised to the power 1 over n. If you have b to the power x, its inverse is log base b of x. And it's pretty easy to actually do the calculations and find that the left and right hand sides are equal. It's not so easy if you want to find the derivative of the inverse of a polynomial. as well as trig and inverse trig functions. Just as a quick sample here, we know that if f of x is equal to the sine of x, then we've been introduced to the inverse sine function, which is the arcsine of x. And if I try to use this formula here to come up with the derivative of the arcsine of x, well, what this formula is telling me is I'm going to differentiate f to get the cosine of x, and then take f inverse and plug it into the variable inside of f prime. So by the inverse function theorem, d dx of arcsine x, the derivative of arcsine x, would be 1 over the cosine of the arcsine of x. Now this is incredibly ugly. We do not want to have to work with this thing. We're taking compositions of trig functions and inverse trig functions. We don't really want to work with this particular kind of thing right here. We don't want the function itself appearing in the derivative of that same function. So we're going to use the technique of implicit differentiation to help us figure out a much nicer formula for the derivative of arcsine x, arccosine x, and arctan x. We're going to see what these three things, we're going to see what their derivatives are going to be. We're actually going to go through the proof, if you will, of one of these. The other two use the same kind of process, the same kind of tricks. So we're going to go through the derivation, if you will, of the derivative of arcsine x. So if y is equal to the arcsine of x, or the inverse sine of x, then dy over dx is going to equal what? So y equaling the inverse sine of x, I can take the sine of both sides. So I get the sine of y is equal to the sine of the inverse sine of x. Well, sine and inverse sine are inverse functions of each other. When you take the composition of a function with its inverse, you just get the argument. You just get your variable, which in this case is x. So if y equals the inverse sine of x, then x is equal to the sine of y. This is where the technique of implicit differentiation comes in. I'm going to differentiate both sides of this guy with respect to x. If I differentiate x with respect to x, I just get 1 equals, and now if I differentiate the sine of y with respect to x, again, I'm differentiating a y, so I'm going to pretend that there's nothing fancy, nothing special with it. Pretend it's just your average normal variable, but then multiply by dy over dx at the end. So I'm going to get a cosine of y times dy over dx. And that means that dy over dx is equal to 1 divided by the cosine of y. Okay, so we've begun to get something to equal dy over dx, but we have this thing in terms of y's. We want something in terms of x. Our given function was in terms of the variable x, so we want to leave a final answer. in terms of x. Well, now we're going to appeal to the most commonly used of our Pythagorean identities. We know that sine squared y plus cosine squared y equals 1. This is all side work here. So this means that cosine of y is going to equal the square root of 1 minus sine squared y. So this means that dy over dx is equal to 1 divided by the square root of 1 minus sine squared y, which is also same thing as 1 minus sine of y squared, right there. These are just two different ways to say that same thing. All right. Well, if we take a look back earlier on in this process, we saw that sine of y is equal to something in terms of the variable that we want. Specifically, sine of y is equal to x. So I'm going to take that variable x, and I'm going to substitute it in here. And I now get dy over dx in terms of my variable x. We finally see that dy over dx is equal to 1 divided by the square root of 1 minus x squared. So this is just a little outline of what we just did in a little bit less detail, but still the same outline. And just looking at it, it's kind of odd or kind of interesting that the derivative of an inverse trig function doesn't involve any kind of other trig happening in there whatsoever. We get 1 over the square root of 1 minus x squared. There's no sines or cosines or anything of that sort popping up. But that is how we can derive the derivative of the inverse sine of x, or arcsin x. Finding the derivatives of arc cosine x and arc tan x require the same kind of method overall. You're going to take the cosine or the tangent of both sides. You're going to implicitly differentiate. You're going to use a Pythagorean identity, and then you're going to make a substitution back. And you find that the derivative of arc cosine x is minus 1 divided by the square root of 1 minus x squared. And you find that the derivative of arc tan x is 1 over 1 plus x squared. So these are the three most common inverse trig functions that we see popping up. These are the derivatives that you, again, just have to memorize. Brand these guys into your mind. Say them to yourself so many times that you can repeat them in your sleep. So we're going to throw these guys into the bag of functions that we know how to differentiate and can show up on future quizzes or tests. So this was our quick and fairly short video on derivatives of inverses of functions, specifically derivatives of some inverse trig functions. If you guys have any questions, be sure to leave them in the comments section below. Feel free to drop comments down there as well. And until the next video, guys, take it easy.